A reminder about heat diffusivity equation with constant K. Of course, in the Cartesian geometry. Now, when we don't have any heat generation in the system, so this is going to be 0. This is no heat generation. Within the medium that we studied, the heat conduction, if you are dealing with the steady state, there is no change in time. There's no change in time. And what we have here, we ended up is the only term is going to be the second gradient of temperature. And since this is now an ordinary differential equation, you can write it T0. If you take the integral of both sides, what you ended up here is dt over dx is constant. And this is Fourier's law. I'd like to go through a few examples here on using this heat diffusion equation for various conduction problems. One of the equations that I just written down here is we would like to find a steady state temperature profile in a plane wall of made in glass fiber. There is no heat generation within the wall, and the inner side of the wall is at 100 degrees C and the outer side is at 20 degrees C. The wall thickness is 20 centimeter, find heat flux in the middle of the wall. So for all of these heat transfer problem, everything in this class, we are gonna follow the procedures given in section 1.5. So we follow the procedure for analyzes heat transfer problems in section 1.5. Please go and review that section. So if you look at that, the first things that we do is we list all knowns. So what are knowns for this problem? We know the temperature at the inner side is given. T1 is 100 degrees C. The temperature at the outer side of the wall is given by 20 degrees C. And the wall thickness is 20 centimeter. So L is 20 centimeter and yeah, this is given. And we know that the wall is made of fiberglass, of glass fiber. Glass fiber. Now we can read K from the tables at the end of your book. So there are a few tables at the end of the book that list all the thermophysical properties of a lot of materials at different conditions. So if you read K from that one, it's going to be about 0.035 watt per meter Kelvin. So these are the knowns. Now, the other step is always to draw a diagram. That helps a lot for the problems that we are going to look. So we have a wall. This is x equal to 0. This is x equal to 20 centimeter. This is the thickness of that. One side of the inner side is T1. T1, which is 100 degrees C. The outer side, T2, is 20 degrees C. And what we have been asked is finding temperature distribution as T of x, heat flux in the middle of the wall, which is Q double prime at x equal to 10 centimeter. These are what we have been asked. And assumptions. Always list your assumptions as a part of the step. We assume this is steady state. I guess it was given in the problem. Yeah, this is a steady state, but even if it's not given, and there is no mention of time change or anything from sometimes the type that the question has been narrated, you may find out this is the case, and there is no heat generation. So these are the two assumptions. These steps are the ones that I want you to follow in all your assignments, quizzes, exams, whatever questions that you have been given. I would like to see that as a part of the way that you're working out the problem. Now, always start from the general form of the either energy balance equation, or if you have the simplified version of that, always start from that part. So for this case, we are dealing with the plane wall, semi-infinite in the two other dimensions, and we can use simply the energy balance equations in the x direction that you know the equation reach to heat conduction equation or heat diffusion equation. So I'm going to use that one. So starting that, just going to write through here 1D heat diffusion equation. So write in the general format, which is d2 dx2 plus q dot k rho c dt dt. Now, since you know this is a steady state, this term is going to be 0, no heat generation, this term is going to be 0. So why you ended up here is, so we simplify this equation based on assumptions that we have, based on these two assumptions. Now, what we ended up is d2x x2 equal to 0. If you take an integral, it's going to give you dt over dx is a constant c1. And the second integration gives you t as a function of x. It's going to be c1 c1x plus c2. Now we need to find c1 and c2. This is a second order ordinary differential equation, so we need two boundary conditions. So we need two boundary conditions. Now, for boundary conditions from the problem, we have two constant temperature at both sides of the wall at two x locations, 0 and 20 centimeters. So these are going to be our boundary conditions. We know that T is equal to 100 degrees C at x equal to 0. And we know T is equal to 20 degrees C at x equal to 20 centimeter. So these are our boundary conditions that we have for this problem. If we implement these boundary conditions at x equal to 0, T is 100. So that gives you C2 equal to 100. And if you replace that, and I'm gonna do that anyway. So 20 degrees C is gonna be C1 times, this is in centimeters, so I'm going to be careful and put it 0.2 in the form of unit of meter, because your K is in that unit, plus 100. From here, C1 gives minus 400 degrees C per meter. Now, this is the unit of that. This constant is degrees C. If you replace them, you can get the temperature profile. T of x is going to be minus 400x plus 100. If I plot, so let's say this is the wall that we were looking at, and generally I use that as a plotting. This is x, this is 0, this is 20 centimeter. And if I make this one like the temperature axis T. So I can plot that this is 100 and this is 20, and it's a linear line. Connecting these two together. So we have a linear temperature distribution in this case. Let's find out what is the flux. Okay, Q double prime is, if you recall, it's going to be Q over A, which is going to be minus KA dt dx. I'm using the Fourier's law divided by A, which is minus K dt dx. Now, Q double prime at x equal to 100 centimeter. This is what we have been asked. It's gonna be K was minus 0, it was 0.035. It had a unit of watt per meter Kelvin. This is gonna be K times dt dx. If you take the derivative, it's gonna be minus 400, which had the unit of K over M. So we are ending up, if you do the multiplication, it's gonna be 14 watt per meter square. So this is the flux. And there are a few things that I'm gonna list here before going to the second problem, is that one of them is heat flux is constant. It doesn't really depend on where we are measuring that. Even like at any X location, the heat flux that is going per unit area is going to be constant here for this problem. So the heat flux constant in the direction of heat of transfer for 1D steady state conduction problem without actually heat generation, and the other one is in Cartesian coordinate. This is one of the things that I would like you to pay attention to that. And the second one is we can always use this Fourier's law that we have we can always use Fourier's law to compute heat conduction rate from the temperature distribution. And the other one is no heat generation accommodation means Q in equal to Q out.